Okay, so today we're going to have Dewald van Heerden talk to us about modeling covalent intermediates of the nitrilase superfamily. Dewald graduated with his PhD at Stellenbosch University under the supervision of Len Barber, and he studied computational physical chemistry in relation to small molecule structures. So getting into big molecule structures and enzyme mechanisms was a huge departure for him, but he has managed to master the quantum mechanics of enzymes' active sites, and he's done something that I think is astonishingly innovative. So I think that we're in for a treat as he explains a different way of looking at enzyme active sites based on the stereochemistry of the intermediates. Okay, over to you, Dewald.
All right, thank you very much, Professor. Setting the bar quite high, but yeah, yes, thank you for the opportunity to present at this month's colloquium. So to get straight into it, let me just get, there we go. The next slide. So nitrilase enzymes are thiol enzymes that catalyze the hydrolysis of nitrile compounds to carboxylic acid, to the corresponding carboxylic acid and ammonia. They have a wide range of industrial applications and biotechnological applications, including the synthesis of industrially important carboxylic acids and bioremediation of cyanide and toxic nitriles. So, as an example, there's high sequence conservation among these three pyrocarpyl nitrilase superfamily enzymes, and the black rectangles show the highly conserved residues that make up what is called the catalytic tetrad. That consists of a cysteine, and a low numbered and a high numbered glue, and a lysine. So again, as an example from this pyrococcus amidase crystal structure, just showing the relative orientation of the active site that makes up the majority of, or basically all of the all of the enzymes that make up this superfamily of enzymes. So there are two reactions that pertaining to the enzymes making up the superfamily, and so the so-called nitrilase and amidase reaction. And in this talk, I'm mostly focused on the amidase reaction. However, the intermediates of the hydrolysis of the nitrile will also come up in the presentation. So just to kind of point out the important bits, the thiol enzyme in combination with or with a water molecule coming in forms the thioimidate covalent intermediate. And then with the second water molecule coming in with an ammonia or ammonium being released, i.e. the nitrile nitrogen, you form the thioester or the so-called acyl enzyme intermediate. And then with another water molecule coming in, you hydrolyze the thioester to finally give you the carboxylic acid. And the amidase reaction is just starting straight away from the amide. And yeah, so I think it's called the nitrile hydrolysis that basically gives you the amide as the final product. So yeah, most of the talk will focus on the amidase reaction. In 2000, it has been, the following reaction mechanism has been proposed, in that the low number glue first deprotonates the thiol to give you the thiolate, and the thiolate is then a stronger nucleophile to attack the carbon of your amide substrate, which then forms the tetrahedral intermediate. And once the tetrahedral intermediate cascades back, you basically get ammonia forming with the thioester, and of course the reformation of your protonated glutamate, low number glutamate. However, we think this is quite unlikely due to the very low pKa of the glue, which is around 4.7. So we would like to propose, or we set out to propose that it's the neutral thiol that does the nucleophilic attack, with the thiol hydrogen being activated, kind of with the pre-existing hydrogen bond with the glue. So instead of first deprotonating the glue, the thiol, we form this highly charged tetrahedral intermediate, which then collapses again to give you the thioester intermediate and ammonia. So in order to, where am I on my slides? To test this hypothesis, we initially decided to basically scan this deprotonation step by stepping the thiol proton from the cysteine all the way over to the low number glue, by systematically decreasing the oxygen-hydrogen bond distance. And the resulting energy profiles are as follows. So depending on the size of the active sites, so increasing from just having the glue and the cysteine, the low number glue and the cysteine, gives you the little blue charge. So of course, at 2 angstroms oxygen proton separation, this is where the thiol is. So we basically step in the backward direction until you form the glutamic acid and thiolate, and then you I step it all the way down to 0.9. So you enter into the highly repulsive territory. So it's quite interesting to see that the exact catalytic tetrad, namely the 2 glues, the lysine and the catalytic cysteine, gives this quite unique profile. Whereas adding a tyrosine that's hydrogen bonding to one of the glutamates, gives you the same profile as the one without the second glue. However, improving the basis set quality from the low basis set quality on the left-hand side, we definitely see a distinct energy barrier for the transition. However, there's no real clear preference between whether it's the thiol on the right or the thiolate that's on the left-hand minimum of this graph. However, improving the basis set to a triple zeta instead of the single valence polarized basis set, you most definitely see that the protonated thiol is the most favorable state. So moving on to the usual normal next step is to conduct docking studies. However, the conventional docking packages such as AutoDock or UCSF Dock only relies on the atomic coordinates to automatically give you the force field atom types and the corresponding energy terms to solve Newton's classical mechanics equations to give you an energy value for your system. However, Tristan, who I've been in contact with and has been a great help in setting up the procedure, which I'll explain now, developed this ISOLDE package that that included or can be included as an add-in to the UCSF ChimeraX software ecosystem, let's call it that. So if you just have a normal substrate, you can in the ChimeraX / ISOLDE GUI that's in ChimeraX, you can just select that substrate. So not like bonded to anything, it's just hydrogen bonding is the highest level of interaction. And it will run a little anti-chamber script in the background to give you the amber force field atom types and semi-empirical charges. And then using OpenMM architecture, it will, as I said, solve Newton's laws to compute the forces involved in the making up the macromolecule. And of course, this is or it's coded in such a manner that it's GPU intensive, not so much CPU intensive. So just as an example, I will discuss the results for the nitrilase isolated from Pseudomonas fluorescens. This enzyme has been shown to convert a broad range of aromatic and aliphatic nitriles, and can also conduct the enantiomer selective synthesis of various aryl acetic acids. So just an overlay of 3 of the catalytic tetrad of some nitrilases and cyanide dehydratase, showing you that although the residues in between these catalytically active residues might differ, how the protein folds, they're always in very close proximity, forming this highly polarized or highly electrostatically polarized environment for the substrate to react. So the chiral ligands that we docked into the DFNet protein are the phenylglycine nitrile and mandyl nitrile, and the corresponding RNAs, of course, and the corresponding amides. Is it working? I hope it's working. This is I captured this little video screen grab on my laptop, which is not the strongest GPU orientated machine out there, so it's quite jumpy. However, it's just as a way of illustrating the process that ISOLDE uses via molecular dynamic simulations to minimize the energy of this docking system, and which is something that's in the title. You can actually interactively, let's say, participate in the minimization process by tucking atoms or tucking the complete residues or certain atoms that you select. And what is quite important also for these nitrilase superfamily enzymes is that the nitrogen nitrile or the oxygen of the carboxylic or the carbonyl oxygen of the amide are always situated in the what's called the oxyanion hole. And the oxyanion hole is formed by the let me see if I can get a pointer and laser. So this is the lysine. This is one of the glues, and the other glue is there in the back, and there's the cysteine. So the oxyanion hole is always formed by the lysine, the catalytically active lysine, and the residue that's one up from the cysteine, that backbone amide, is one of the hydrogen bonding anchors, and the lysine is the other anchor that other than nitrile nitrogen or the carbonyl oxygen of the amide is interacting with. So all 4 of these substrates in this protein, and of course many other substrates in many other proteins, I've placed interactively in this manner using ISOLDE. So this is just in addition to the wild type, we also have experimental data, and then I just like in silico performed a mutation for substituting a phenylalanine for an alanine in this position that's one up from the catalytically active cysteine, and there's also replacing this massive tryptophan with a much narrower, shorter lysine, and there is a way to there's an API that I'm in the process of figuring out, that you can extract the energy values from ISOLDE when you have the simulation paused. It's not yet implemented. So at this stage, the only like kind of energy indicator that I extracted are the bond lengths from the lysine nitrogen and the backbone amide distances. So for the substrates relative to the wild type distance, these are the change in distance for the two mutations, with blue indicating a closer interaction and red indicating a longer, and therefore one would assume, not necessarily assume, but because there's many things in the background, it might also not necessarily. So yeah, so this is just a preliminary indication of the strength of the interaction. It's not necessarily stronger, because there might be something that gets bumped closer or further away, a bit further, and along the line that might change the energy values. However, in general, we see that when the phenylalanine replaces an alanine, that the distance to the backbone are generally a bit elongated, meaning because of the massive phenyl ring, the phenylalanine residue, the molecule, the substrate can't get into the oxyanion hole as close as it did with just a small alanine there. And similarly, when the tryptophan is replaced by a lysine, the substrate can actually enter, or like fall further into the oxyanion hole. So that's just normal docking. However, we're actually interested in modeling the entire reaction pathway, and that would necessitate modeling of the covalently modified residues. And again, this is not something that's currently standard plug and play and built into ISOLDE. So had to, with the help of Tristan and some other people, had to figure out a procedure to actually do this. But of course, the most important, or what makes it so difficult, is that you can't simply pull parameters out of the sky and assign it to your specific residue. It has to fit into the makeup of the entire standard force field, in this case amber. So in order to do that, you have, so this is R represents your covalently modified residue, and you have to cap it with this acetyl and N-methyl capping groups, and they specifically have to have these charges so that they can fit into the rest of the amber force field. So yeah, there are a bunch of text files involved where you can specify based on atom numbers which atoms point charge, which atoms charges you would allow to be modified, and which are fixed at these values. And this is performed using amber tools to generate the classical mechanics force fields, parameters like bond angle and radial angles, and of course the charges of these atom types. So the actual procedure is as follows, because so specifically these levels of theories have to be used, because this is how the amber force field was actually parameterized from the start. So although they are way fancier, specifically basis sets, nobody really likes the Popple basis sets anymore. But because the rest of the amber force field has been parameterized using these basis sets, I want to say back in the 90s, but don't quote me on that. You kind of have to use them as well to fit into the rest of the force field. So first you do, so yeah, so I used Gauss view to draw the capped residues, and then Gaussian 16 to perform these calculations. So first you do a geometry optimization, and then you do a single point at this level of theory with the Merz-Coleman and population analysis. And then you use, in the Amber tools, you use this command to extract the ESP, basically a table, and depending on the Merz-Coleman like grid of charges, and then you use antichamber to obtain a resp charge dot charge file, and this file is then basically if you have, let's say, 32 atoms in your capped residue, you will have 32 values in columns of 8 of a length by 8, by the way, in this file. And the input file that you give to antichamber, in that input file you indicate with a 0 that it is something that the algorithm needs to find the charge from the esp.date file. Otherwise, you give it let me just go back. You give it this value, and then the program knows that it doesn't have to find that value. That's how you ensure that the capping group charges can be subtracted at the end. So then you get a Z matrix after removing the capping groups, with again a couple of steps involved to get like a prep-in file that you then give to parameter check to obtain the general amber force field. Or basically the missing general atom force field types is then assigned to your specific residue. So then you get a modified force field file, and then you also need to get a structure file. And in our case, we selected the mol2 format, and then you combine the structure and the parameter files into a force field XML file, and then with parmate, which is a Python model, you combine it into this XML file. So I think you just have a little extract from the force field file to so this lists the atom types, and then below this is the bond types, and then below the bond types you are assigned your harmonic force constant, and also the angles, and so forth. And of course, each atom type has its own, based on the electrostatic potential charge assigned to it. So now basically you can open this, you can open your PDB file. You can. It's highly recommended that you do import your electron density map, and then you can. Then initially it will say that it can't recognize this covalently modified residue, but then you also upload this force field file, and then all standard amino acid residues and your new covalently modified residue can be handled by OpenMM, and then you can minimize your structure. So just as a reminder, I don't think I have blocks that come up anymore. We are looking at the thioimidate, which looks like that, intermediate, and also a thioester intermediate that looks like that. And so, for example, did I say everything that I wanted to do on that? No. So in conjunction with the electron density map, we successfully minimized, using the amber force field, these covalent intermediates for the thioimidates in blue and the thioesters in gray. Of course, using the solder. So this is kind of how far, let's say how far I've got in the process. Of course, these force field minimized structures can now be used as superior input files, as opposed to just ab initio placing or like making up these intermediates. However, now we have much better input structures for higher level quantum mechanical calculations to further investigate the reaction pathway. So just as a showcase of what we have been doing, towards the publication, is to another very important component that I've left out of the talk so far is, of course, the water molecules that have to come in to initially hydrolyze the nitrile to form the thioimidate intermediate, and then to hydrolyze the thioimidate intermediate to form the thioester intermediate, and then to hydrolyze the thioester intermediate to eventually reform your enzyme, and then the carboxylic acid and ammonia. These calculations were initially started by Gerard Venter at the chemistry department, and then I repeated that and built on it again. Just as a way of showing what also a lot of time was spent on is these QM-MM calculations, which use the ONIUM architecture in Gaussian to assign certain residues to the high level of calculation, in which we use the omega p-XT density functional, and then the rest of the entire protein, instead of doing things in vacuo, then you have the protein surrounding your QM region, and then depending on whether you use mechanical or electrostatic embedding, you can polarize. You can use the molecular mechanics shell to polarize the wave function of your QM region. However, just as a overview, or like it's always nice to get pictures in the end, and one of the nicest pictures that quantum mechanics calculations can give you are orbitals. So in this instance, we were interested in positioning the thioester and the water molecule, and in this case, we found the lowest, most favorable configuration of the water molecule is in hydrogen bonding with the low number glue, and the backbone carbonyl of the residue that's following the in this case it's just adenine, but it doesn't really, the side chain doesn't really matter. However, from the NBO analysis, we see that there's a p-type orbital that overlaps with the pi antibonding orbital of the carbonyl. So there's the carbon and the oxygen. So this shows that the water molecule is appropriately aligned for the nucleic attack of that carbonyl carbon to break the carbonyl oxygen, to break that bond, and eventually forming the carboxylic acid. So in summary of the talk, I think I'm doing way too good for time. We found that from stepping the cysteine protein from the thiol to the glutamate, forming the thiolate and the glutamic acid, that the thiol is actually more lower and more stable. So that kind of lends credence to our proposed mechanism, where it's the neutral thiol that does the initial nucleophilic attack on either the nitrile or the amide substrate. We also successfully did docking type minimizations using ISOLDE, so that's plug and play. However, to further model the reaction pathway and to obtain structures for subsequent higher level theory calculations, we derived the procedure to parameterize covalently modified residues. So modeling the reaction pathway is on our way, i.e. getting transition state structures and the relative energy values involved. So finally, of course, I just want to acknowledge some important people. As I've mentioned, of course, Professor Sewell for hosting me in this postdoc at ECT. and Hira, that's been a great help from the chemistry department, and NRF for funding, and finally, thank all of you, the audience, for your kind attention. Thank you.
Thank you very much, Dewald. May I start with well, I'm going to give myself the privilege of starting with the first question.
Okay.
What do you think of the idea of using the water molecule that is frequently observed, hydrogen bonded to both of the glutamates, to convert the incoming nitrile directly to an amide?
Yes, because I'm not sure how. Yeah, I think let's just go. I think it's like slide number 3. Oopsie, I should send this chat to everybody instead of going to slide 3. Slide 3. One more, one back. So yes. So instead of forming the instead of forming the thioimidate, you immediately from the nitrile form the amide, and then the amidase reaction proceeds. I like that idea more so than the formation of the thioimidate, actually. But of course, at this stage, I don't know which it would. Yeah. Ideally, I would be able to tell you eventually which pathway has the lowest energy barrier and would be the peripheral pathway. But yeah, I see what you mean, and I would like to model that and compare it to the, as far as I understand it, the currently accepted formation of the thioimidate first, and then the hydrolysis of that to give you the thioester intermediate.
I want to ask one other follow-up question. How would you account for the fact that in some of the mutants that were discovered by Eric Eppinger, the majority of the output of the enzyme was actually an amide and not an acid?
I.e., kind of like a nitrile hydrolysis reaction mechanism. I'm a bit what's the word? Underexposed to the literature on nitrile hydrolysis. That will actually be a really, really great starting point, I suppose, to see if there are potentially, if the reaction pathway of the hydrolysis are well modeled quantum mechanically already, and then it will be, if that is the case, it will be ideal to use that as a starting point, in our case, to kind of mimic that in the formation of the thioimidate, to then eventually form the carboxylic acid via the thioester. So this actually lends credence to Prof's first question, in that maybe the formation of a covalently modified cysteine intermediate isn't that involved, and it's simply the highly polarized environment of the active site pocket that with, of course, with the water being doubly charge assisted hydrogen bonded to glutamates, glues, to then actually make it highly nucleophilic to attack the nitrile carbon. And
I think that you've got an open field here. You can just wade in because there's no competition.
Okay.
Now you've told everybody the secrets.
Yeah, well, the most power from science comes from collaboration, as opposed to, I don't know, writing a novel on your own, I suppose, and hoping you hit gold. Science is collaborative, so ideally, the more people know what you're up to, the more they can also do things, and then you can together build knowledge.
Okay. Does anybody else want to ask a question?
I have my hand up.
Okay, ask away.
So 2 questions about just sort of methods. One is, if you use QM would you expect to see some different results from if you use quantum dynamics? So like a Parnell type method, or do you feel like that? I guess the way to say it is, do you think things are missed by not explicitly including the dynamics in the method? That's one question. And then the other question is, have you thought about explicitly exploring isotope effects, like so deuterium effects, in your quantum methods, in your quantum part?
Let me answer the second one first. I can explicitly say no to that. However, the idea is to kind of still, so doesn't quantum dynamic the like resource requirements, of course, it's coming down all the time, but I don't think it's currently yet at that stage where it can compete with these QMMM procedures, in a sense of I think at this stage that QMMM approaches like ONIM, that's the only one I've ever used. I'm not, I've not like had to rely on others, but I do think, but of course the QMMM approach would still be at 0 Kelvin in kind of in vacuo. You after the fact, as an add-on type manner, then introduce the MM shell. So I don't know what the computational limitations is of the quantum dynamic approaches at this stage, whereas we already run into trouble with the size of the QM region in the QMMM calculations. So going one rung up in the computational hierarchy, I suppose, would open one up to even more nitty-gritty error messages. So, but yeah, the idea of the QMMM calculations is indeed to not simply have stuff floating around in vacuo, but to actually do have it surrounded by as close an approximation as the environment that it would be in vitro. Well, yeah, in a living organism, of course. Yeah, so these I've also run these surface scans in an implicit water molecule and implicit water model. So instead of actually placing explicit water molecules around your residues, in an implicit water molecule, it basically places an dielectric field around your model to modulate the polarization of each of the covalent bonds, and that does actually already have a quite large influence on these profiles. And I must say, at a small level of a small basis set level, the single valence polarization basis set, including an implicit water model makes it look more similar to the higher level of theory, i.e., much larger basis set already. So just accounting for an dielectric field type environment already has an influence on these energy profiles. So yes, including quantum dynamic effects will definitely have a large effect. I'm just not sure how limited one would be in terms of resources to perform such runs.
Okay.
Thank you.
Thanks.
I think I also want to make a comment here, and that is in the force field minimization, the electron density map, the actual measured electron density map, is included in the force field. So we're modeling against a background in which experimental observations are included when we do the molecular mechanics. We don't have the infrastructure to do any quantum dynamics.
Yep.
Okay.
Okay.
Yep.
Okay. Am I missing? I can only see about 6 people at once. So if you stick your hand up, you better speak. Okay. Are there any other questions for Dewald? Okay. Well, I just want to conclude by saying that if anyone wants to actually model putative covalent intermediates and make the amino acids that are formed by covalent intermediates, they should write to Dewald, and he can send you the files so that you can plug in your own covalent intermediates into your own enzymes. It's quite a fun thing to do. Okay, with that, I think I'm going to close the meeting. Thank you all for coming.